Howdy guys, so in this video we're going to look at the principle of mathematical induction. So from the example that we did in the first exercise on the process of induction, so we use that Pn to represent a proposition which is defined for every integer n where n is greater than a, so that, and a is within z. And as we discussed before, this z means all integer numbers, so from negative infinity to infinity. So for example, in the case of example 1, our proposition Pn is that 1 over 1 times 2, all of those things give us this for all n within z plus. This means positive integers, so 1 through to infinity, essentially. And we saw that when we did it with P1, that's when n is equal to 1, gave us a half. Then we had when P2, we got 2 over 3. And then if we did Pk, we would get this. So this is if we had pk, the kth term, I suppose, kth term. We would then change these n's to k's and we'd get k is equal to k plus 1. Now you're probably wondering why would we do that? And you're going to see that more as we do some examples as we come down. But what you'll see when you do mathematical induction is there's two main steps. And the first one is always to use our very simple first case, which is this one here. This is what we call our basis. And then we also use this k, so when we swap the n to be k, and this is sort of like our induction step. And when we get to some examples, I'll show you a little bit more on how that works, and I think it will make more sense. So the principle of mathematical induction constitutes a formal proof that a particular proposition is true. So suppose Pn is a proposition which is defined for every integer n greater than or equal to a, and a is within all integers. If pa is true, and if pk plus 1 is true, whenever pk is true, then pn is true for all n greater than or equal to a. Now at the moment that probably sounds like a whole heap of jargon, and that's okay. As we do this more and more and we look at more examples, it will become clearer. But if we have a look down here, so it says, suppose for a given proposition that P1 is true, if we can show that PK plus 1 is true, whenever PK is true, then the truth of P1 implies that P2 is true, which implies P3 is true, which implies that PK is true, and so on and so forth. And that's because if you think about it, we would have P1, P2, P3, and if we kept going, we get to PK, and then we get to pk plus 1. So what it's kind of saying is if we know that P1 is true, so this one is true, if we can show that, and this is what induction is, showing that this one is true, whenever we know pk is true, or we assume pk is true, then what that means is that the truth of P1 implies that P2 is true, P3 is true, and then P4 is true. So if you can show that this one works, it will prove that they all therefore are true. So to kind of give a scenario, one can liken the principle of mathematical induction to the domino effect. We imagine an infinite set of dominoes all lined up, provided that the first domino topples to the right. So imagine that first domino falls over, this one here. The kth plus 1 domino will topple if the kth domino topples. So if we say that this is the kth here, we know that if the kth topples, then the kth plus 1 will topple. Then given sufficient time, every domino will topple, because if you think about if this first one topples and then the kth, sorry I didn't say that, we'll say this one's the kth, and then the kth plus 1 topples, that means all of these in the middle here also topple, which is essentially the idea of induction. Now if you're still confused by that, let's have a look at an example. Alrighty, so here's our first example. So we want to prove that this wonderful looking equation here is equal to that for all n within positive integers. So the first thing you always need to do is create a statement, which is your proposition or your conjecture. So to save us some time, I just wrote it out. So this is our proposition. So our proposition is essentially almost kind of restating the question, but it's saying that Pn is blah, 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 blah for all n within the positive integers. Now we get on to, I suppose, our first step of the proof. So if I just write proof here. Okay, so our first step is what we call our basis step. And as I spoke about before, the basis step is the first and most simple version that we've got. So our simplest version is going to be that if n equals 1, now if we're looking at 1, we're looking at the first term. which is obviously this one up here. So what we could say is we're going to have the left-hand side is equal to 1 squared, which is equal to 1. Okay, so we've got that. Now the next step is we also need to look at the right-hand side. So if we look at the right-hand side, so we know that n is equal to 1, so this is our right-hand side, so it's going to be equal to 1, 1 plus 1, 2, 1 plus 1, over 6. What's that going to give us? 2, 3, 6, which is going to give us 6 over 6, which is equal to 1. So you can see that both the left-hand side and the right-hand side are equal to the same thing. So therefore we can say that P1 is true. Okay, because it works for both sides. So if n is equal to 1, we're looking at the first term here. We've got 1 squared is equal to 1, and then if you sub into the right-hand side, you get 1 as well. So we can say that P1 is true. Now that's the first step that you need to do. Okay, now we get onto our second step, which I like to call the induction step. So I'm just going to do it down here. So we've got induction. Now the first thing we need to do on our induction step is assume that pk is true. So we do that by saying if pk is true for k within the positive integers, then we can say that we can use a summation if we want to. So summation of k, I should say k, not n. So 1 of I squared is equal to 1 squared plus 2 squared plus 3 squared plus all the way to k squared. So remember we had n's originally, but now we're saying pk. So because there's a k here, it's not n, we're changing all the n's to k, is equal to k plus 1, 2k, I should say, 2k plus 1 over 6. So we've essentially changed all the n's to k's, and we're assuming that this is true. Now I've just given us a bit more space. Now what we need to do now is we need to look at the k plus 1 scenario, and we're going to use the fact that we're assuming that this is true. So what we've just written here, we're going to assume that this is true and use that to show that pk plus 1 is true also. So now we go to our next step, which is thus we say 1 squared plus 2 squared plus 3 squared plus all the way up to k squared, which we had before, but now we're going to go plus k plus 1 squared because we're finding that pk plus 1. Okay, now if we have a look at what we've got here, we know from above, from what we're assuming, that 1 squared plus 2 squared plus 3 squared all the way up to k squared is equal to this. Okay, so what we can do now is sub this in for that bit there. So we can now say that it's equal to k plus 1, 2k plus 1 over 6 plus k plus 1 squared. So I hope that makes sense. So again, because we know that this bit here is equal to this, we can sub in for this bit. Okay, and now we need to use our awesome algebra skills to try and simplify this essentially. So if we have a look here, what have we got? Well, let's make this one fraction. So if we multiplied both of this here by 6 on 6, we would then have k plus 1, 2k plus 1 over 6 plus 6 lots of k plus 1 squared over 6. So we could then go so hopefully that all makes sense, because we can now put that over 1 common factor of 6 there as a denominator. Now what I'd do now is pull out a common factor of k plus 1. So we could pull out k plus 1, which if you can't see that would be, let's see if I can highlight it, this bit here, and 1 lot of those. So we'd pull that out the front, and then we'd still have, go back to my pen, we'd still have k, because this still exists, so k out the front of 2k plus 1 plus 6 lots of k plus 1. So we only pulled out 1 lot, all over 6. Now let's make this a bit smaller, shall we? Okay, now we'll keep going. So we've got k plus 1, so it's going to be 2k squared plus k plus 6k plus 6 all over 6 is k plus 1. What do we got here? 2k squared plus 7k plus 6 all over 6 there. All right, now we want to try and factorise what's in those that square bracket. So we've still got the k plus 1. Okay, now we're going to think about, well, we're going to have a 2k and a k. And we're going to think about, okay, well, what two numbers are going to give us 6, but then also give us this 7k factoring in this 2. So that's where it gets a bit tricky. We have to think about, okay, well, we know that 3 and 2 is 6 and 6 and 1 is 6. And I think I would, if I was looking at this quickly, I'd go, well, we've got a 6 here. If we multiply 6 and 1, we get 6. And if we add together, we get 7, which is great, but that's not factoring in this 2. So we need to think about that. So we need to get, so imagine that you're going to expand this out to get this one and then this one. We need something that's going to give us 2 lots of that value there. So if we try 3, for example, so go plus 3 and then plus 2, that 3 and 2 here will give us that n term of 6. But if we go that 2 times 3, that'll give us 6 plus this bit here, which will give us plus another 2, which is 8. So that doesn't work because we need 7. So we know that those don't work. Now, I bet you I won't be able to erase all of this. Hang on a second. All right, so let's try it the other way around. So we've still got a plus here. So let's try plus 2 plus 3. So obviously this 2 times 2 will give us 4. So that'll be 4k. And then this k times 3 will give us plus 3k, which we know is 7k. So the 3 and 2 gives us the 6. And the 4k plus 3k gives us a 7. So we know that this is right. Okay, so it's a little bit tricky, and this is where it's really good for your factorization skills. Obviously, if we didn't have the 2 here, it's much simpler. So that's what we've got there. So hopefully you can still see that. I might just write it out a bit clearer. So you've got k plus 1, and then now you've got 2k plus 3 and k plus 2 all over 6. Now this is where we need to be a little bit clever as well, because if you look back up at this original function that we're assuming here, we've got a k, we've got a k, and we've got a k. Now for this to work for the, essentially because this was pk, we're looking currently at the pk plus 1. So what we want to do is make this a k plus 1, and a k plus 1. Now at the moment we can say that we've got a k plus 1 here, but we don't quite have that with these two here. So we've got to think about, well, what can we do to make them a k plus 1 within the rules, of course. So let's think about these. So if we looked at this k here, this one here, we can go k plus 1, that's still the same, isn't it? Because k plus 1 is k plus 2. But now all of a sudden we can tick off that k plus 1 as well. So we've ticked this one, we've ticked this one. Now if we do it here as well, we've got 2k plus 1 plus, now what are we going to have to put in there? Now we need it to be a 1, because that's what they've got there, so it needs to be a 1. But does it work? So if we just think about this at the moment, if we just look at this, I'm going to draw it really small. We've got 2k plus 2 plus 1, which is equal to 2k plus 3, which means it works. So we've got all of these values now with a k plus 1. So we've got the k plus 1 where that original k is, you've got another k plus 1 where the original k is, you've got another k plus 1 where that k is. So now that we can see that it works, okay, we have one final very important step that we need to now summarize everything and make sure that we've done this induction correctly. So we say that since P1 is true and PK plus 1 is true, okay, so PK plus 1 is what we've just figured out here, and P1 was true because we did that in the first step. That was our basis step. But we also need to add on. So since P1 is true and PK plus 1 is true, whenever PK is true. So remember this first step up here for the induction, we're assuming, or we're saying if PK is true, then this is true. And we've used that within the function. So since P1 is true and PK plus 1 is true, whenever PK is true, we can therefore say that Pn is true for all n within z, okay, within all the positive integers. Okay, so when you do these questions, what you need to remember to do, and I might just move everything up, we'll see if everything moves nicely, no guarantees. Okay, So you always got to state your proposition, which was the first thing we did. So state your proposition. Proposition, which was your PN, or you could use conjecture if you want to state your conjecture, which is PN. Then you've got to do your basis step or your base case. Basis step, which is normally your P1. 3, you then need to do your induction, which is, first of all, you need to assume PK is true. And I need to move up again. Oh. PK is true, which is this step up here. And then you need to use PK to show PK plus 1 is true. And then you also need to summarize like we've done down here. Okay, so hopefully that kind of helps, but I know there's a lot going on and it's quite difficult to follow in the beginning. So if you're not quite sure, that's okay. I might even put up another video that you can watch by someone else to see if that helps. I think sometimes seeing it from different people can be really, really good. And I've just realized I haven't quite finished the question, which is find, what was it, 1 squared plus 2 squared plus 3 squared plus 100 squared, using obviously that wonderful equation. So we know that that was equal to, what do we have? I can't read it up the top there. Remembering that it was equal to n plus 1 to n plus 1 on 6. Now in this case, n is equal to 100. So we're going to have 100 times 101, tell if I could write, times, well, that's going to get us 201, I reckon. 201 over 6. So that's just me subbing in 100 where all the n's are. And that should give us, if you put that in your calculator, 338,350. Okay, so a lot to take in. I'm sure we'll do some more as a class as well, or whatever we need to do on Wednesday. Well done, guys.